Hello everyone, I'm Amir and today I'm going to talk about our work called zooming out on an evolving graph. Property graphs are being used to represent many concepts such as social network, transportation network, and web. Graph databases that support property graph models are now part of the mainstream and being widely used for different tasks. The assumption that previous system makes is that they treat a graph as a non-temporal concept, but for many cases like social network, this is not true. And the network structure and node and edges attribute change over time. Hence, we need to have a system to be able to process and query evolving graph in a systematic and efficient way. The work presented here is part of the Portal project. Portal is a distributed platform for querying and analysis of evolving graph. Portal is implemented on top of Apache Spark and uses the graphics library and Parquet data format. Portal implements the T-graph data model and the operators of compositional T-graph algebra or TGA. In this talk, I describe two TGA operators: temporal attribute-based zoom or A-zoom for short, and temporal window-based zoom or W-zoom. These operators zoom out on a T-graph. A-zoom zoom out structurally, while W-zoom zooms out temporarily. Let's now introduce the T-graph model and zoom operators. We show T-graph model in figure like this. Each node or edge have an ID and some key value pairs for each time interval that they are valid. We use close-open intervals to show time validity. The model inherited the close-open intervals from SQL standard. For example, Anna existed during times points 1, 2, 3, 4, 5, 6. Bob existed for time points through 2 to 8, with a change of a school to CMU at time 5. There is also an edge connecting those two at the time point through 2 to 6. A T-graph is semantically equivalent to a sequence of conventional or non-temporal graphs called snapshots. One can record one snapshot per time point or associate each snapshot with time intervals during which the graph did not change. We show such an interval-based representation here. Temporal graph algebra, of which A-zoom and W-zoom form part, operates under point semantics with two underlying properties: a snapshot reducibility and extended snapshot reducibility. A-zoom executes under a snapshot reducibility. Its result can be computed by applying non-temporal attribute-based zoom to each snapshot of the graph. On the other hand, W-zoom makes explicit reference to time, and so is based on the principle of extended snapshot reducibility, where timestamps are made available to operators by propagating time as data. Temporal attribute zoom is a temporal generalization of the node creation operator over non-temporal graphs. Let me recall that non-temporal operator here. Assume that we have a coloration graph built from researchers from NYU, Columbia, and Copenhagen University. Someone might not be interested in how individuals collaborate, but how each institute collaborates with other institutes. Attribute zoom help us gain that ability by changing the structural resolution of the graph. Now let's look at a similar example for temporal attribute zoom over this T-graph. Here on top, you can see Ann, Bob, and Kat are members of NYU and CMU. On the graph, on the bottom, you can see that we created a school nodes from the school values. If, for example, you can look at the node NYU, you can see for time point between 1 to 7, NYU had 2 students, Ann and Kat. But when Ann left NYU, it only has 1 student. We also redirected the edges existed in the graph to point toward the institute and updated their time intervals to show the correct validity between the institutes. In paper, we define these operators in more detail using dataflow which can be implemented using any system that supports those. Okay, what is a temporal window-based zoom? W-zoom is a novel operator implemented and introduced by Portal. It changes graph temporal resolution. This is similar to what we do on our calendars every day. Sometimes we want to have information with a resolution as small as a day. Sometimes we want to have a large resolution like months or day or years. So how does it work? Look at the graph on top. The temporal resolution here for this graph is 1 month, but some analysts want to have a temporal resolution of quarters or 3 months. We using temporal window-based zoom or W zoom, we can do this. In addition to that, for volatile graphs, we can use quantifiers. For example, all quantifiers allows us to observe strong signals, strong nodes and connections that always presented in a volatile graph. While if we use exist quantifier, that allows us to pick up volatile nodes and edges as well. Okay, now let's talk about some implementational details. In this section, we will talk about 3 physical representation that Portal used to implement a T-graph model. The first is a representative graph or RG. This is basically a sequence of non-temporal graphs that we introduced in earlier in the model section. RG is simplest representation to understand, but it's not the most efficient. As you can see, there's too much redundancy in RG, and each node and edge would be stored multiple times. Due to this, RG is not as space efficient and cannot support large graphs. Another representation implemented by Portal is vertex edge or VE. VE implement T-graph as 2-nested temporal relation, each storing ID intervals and attributes for nodes and edges. VE is compact and fast. Another way to implement T-graph is one graph or OG. In OG, one graph would store the whole history of the graph compactly. The way this has been implemented in Portal is that we have one graph graph, and each node or edge in that graph has an array that stores the history and validity of the attributes. For example, if you look at node Bob, you can see that the array corresponding to this node has 2 cells, each storing the information for the corresponding intervals. Experiments. We have few data sets that we use to test Portal. Wikitalk, which is the communication graph between Wikipedia users with 11 million edges. Social network benchmark, which is a benchmark by LDBC console with it can produce different size graph. We usually use the largest with 200 million edges. And n-graphs, which is a word co-occurrence graphs with 1.3 billion of edges. We run an experiment on an in-house cluster with 16 workers, 4 cores in each worker, and 32 gigabytes of RAM. Here, you can see the running time for A zoom and W zoom over different subset of n-graphs. As you can see, RG failed to run for a graph larger than 10 million edges and 164 snapshots, but OG and VE show very good performance. VE takes 10 minutes, while OG takes less than 5 minutes to calculate A zoom. And for W zoom, we are seeing the similar result. We are currently trying to develop a declarative language for T-graphs, and after that, we are planning to work on a multi-operator core optimizer and a benchmark to test this. Another interesting area of research for us is working with other fields on real temporal problems. For example, now we are working with economists on family income data, trying to study income inequality over time. Thank you everyone for listening. This is our source code, and I can answer any questions.